In this video, we're going to talk about a method called implicit differentiation. And it's what we have to do when we have a function that cannot be written in explicit form, meaning we cannot get y by itself. So in this case, we have y squared and y, so we cannot get y by itself to take its derivative. So what we do is we assume that y represents some function that we don't know. So it's like a baby. Maybe it's 3x squared plus 2. Maybe it's x plus 1. Whatever it is, there's something in here. So we're treating it as a baby. Because of that, we do have to apply the chain rule. And we are going to use Leibniz notation just to be a little bit more specific. It's just more descriptive. So when we read this, this is the derivative. It's just another way to write y prime, except in this case, this says this is the derivative of y. And this tells us that we're respecting x. This means x is the variable in the problem. It's going to be even more important in our next video. Something that you may hear about is called the normal line. We're not really going to practice it this year, but you may see it next year. So that if we have let's say a tangent line, the normal line is perpendicular to that. So the red would be your normal line there. Okay, so our first example, this says find the derivative of y. So if we can get y by itself, we do. And then we'll take its derivative, and x will be the variable in the problem. So in this example here, I'm going to subtract my 2x cubed and the 5 from both sides so that I get negative 4y equals negative 2x cubed minus 5. I'm just getting y by itself. Now we're going to divide everything by negative 4. And we see that y equals 1/2 x cubed plus 5/4. So this is an example of a function that can be written in explicit form. And now, since this guy is called y, we can take the derivative of y with respect to x. This just means that's the variable in the function. And if we apply the power rule, we'll get 3/2 x squared plus 0. So if we can get y by itself, we do. Here are the rules for implicit differentiation. You can read all of those if you want. But basically, we're just applying the chain rule. And we're using Leibniz notation with dy dx. That's kind of the basic gist of it. So in this example here, I am going to change this just to make this a little bit less complicated. So let's actually get rid of this x and go ahead and change this problem to y squared minus 3y equals 2x. This is still an example where we'll have to use implicit differentiation because we cannot get y by itself. So if we go ahead and begin, this says x is the variable in the problem. So if it's not an x, it's like a function. So there's a function in here. There's something in there. We don't know what it is, but it could be like 3x plus 1. There's a baby there. So we're going to differentiate it. We're going to leave the baby in, and then we're going to multiply it by its derivative. So we treat this exactly the same. So we'll have 2. This is like the baby that will stay in. It's now to the first power. And then anytime we leave a baby in, then we multiply by its derivative. Now we're going to come to the next term. Again, we're going to differentiate it like normal. This technically would be baby to the power of 0, which is just 1. So we don't need that. But we still have to multiply by its derivative. And then finally on this side, the derivative of 2x is just 2. I don't need to do anything different because this is the variable I was supposed to be respecting. So quick rule of thumb, if something matches that variable, we just take its derivative. If it's anything other than that variable, then we have to take the derivative and then put this dy dx at the end. And now since the direction said to find dy dx, that means I need to get dy dx by itself. So what we can do here is we notice that both terms have a dy dx, so we can factor it out. And we're left with 2y minus 3. And now, if I wanted to get dy dx by itself, I can divide both sides by 2y minus 3. And I see that the derivative of y with respect to x actually depends on y. and this would be my derivative. So in the next example, it actually wants me to find now the second derivative. So that just means we're going to differentiate twice. Same deal though. This is the variable we're supposed to be differentiating. If we can't, if it's not an x, then we have to use implicit differentiation. And here we could get y by itself, but when we do, we would get two functions because we'll have the plus or minus square root. So we would end up having to do the work twice. And really 4 times because we're finding the second derivative. So we'll just leave it like this and use implicit differentiation. So we take the derivative of x squared. X is good, that's the variable we want, so we don't do anything different. Now we're going to move on to the next term. So the derivative of y squared is 2y times whatever the derivative of y is. And then the derivative of a constant is 0. Now we could go ahead and find the second derivative from here. I'm going to go ahead and get dy dx by itself, just because then our second derivative, we won't have to actually solve it. So if we take 2x to the other side, we see that we get 2y dy dx equals negative 2x. Now we can divide both sides by 2y, and we see here that the first derivative equals negative x over y. Now we're going to find the second derivative. So the second derivative, and that's just notation for second derivative, here I am going to have to use quotient rule. So I start in the top, work my way to the bottom. The derivative of negative x is negative 1. And that's an x, so we're good. And then the denominator is going to drop down, and we're going to subtract. And now we're going to go bottom to top. So the derivative of y is 1 dy dx. And then since we're going up to the top, the negative x this time will drop. And it's all going to be over the denominator squared. So this is my second derivative. I typically don't like to leave a derivative inside of a derivative. But luckily, we know exactly what dy dx is. If I get rid of all this green here, we can see that dy dx is really equal to negative x divided by y. So I can replace that right here so that my derivative is in a little bit friendlier form. So I'll have negative y. I'll have minus negative x over y times negative x all over y squared. And we could simplify that to a much better answer, but for now we'll just leave it.